Thank you for your kind introduction. Yeah. Today I'm going to present about the work I have been doing on the laminar soil box, specifically related to bidirectional shaking, uh, which we have a bidirectional shake table. So this work was performed with Professor Ramin Motamed, and I am a postdoctoral scholar at the University of Nevada, Reno. So first of all, I would like to acknowledge the financial support from the Department of Energy and collaboration with the Los Alamos National Laboratory. And most importantly, I would like to thank the UNR laboratory staff and students who helped me build the soil model inside this big soil box. So this is my presentation outline. So it consists of introduction, large-scale soil model preparation, the input table motions, and then the comparison between 1D and 2D shaking, and finally conclusions. So usually in site response analysis practice, the soil profile is usually idealized as a 1D model, such as in programs as many of you have used in deep soil or shake. However, the recorded motions are usually in three directions, 2 horizontal and 1 vertical. And these horizontal components are usually applied separately at the base of the soil column as a 1D shaking to get the response at the soil surface. So my research deals with the question, what is the effect of applying these horizontal components simultaneously, and what is the response of the soil in that situation? So to understand the effects of bidirectional shaking or 2D shaking, so if you can assume a 3D model, this is a finite element model built in Palestina, and if we subject this model to 2 horizontal shakings, then we can assume that this soil model will move in the direction as shown by this orbit plot. So in this scenario, the soil is subjected to a multi-directional stress path, and now the response will depend on the amplitude and the phase difference between these 2 horizontal components. And since soil is nonlinear, the superposition of 1D responses may not truly represent a 2D response. So with this motivation, my research objective is to perform the shake table test on soil model at full scale under both 1D and 2D shaking, and then evaluate the effects of 2D shaking on nonlinear soil response. So you can see the picture of the laminar soil box, and it sits on top of a biaxial shake table. The box is 15.5 foot in height, and at the top it's around 21.5 foot wide. So you can see me standing next to the box for scale. So to fill the box, we used soil, which is the Class A bedding sand. So this is a local soil that is sourced in Reno. So you can see the particle size distribution curve as well as the picture of the soil. The table on the right shows the typical soil properties for this soil. I would like to highlight that this soil is a well-graded soil, and it has a maximum dry unit weight of 19.9 kilonewton per meter cube, and an optimum moisture content of 10.5%, which was obtained from the modified Proctor test. So for the model construction, first of all, we used a loader to load the soil into this big hopper, which has a capacity of 10,000 pounds of soil it can hold at a time. And then we transport this hopper into our lab using a forklift, and then we use an overhead crane to lift this hopper. So you can see there is a door, the trap door at the bottom, which is hydraulically controlled. So if we open this, then we can distribute the soil inside the model box, and we use this crane so that we could distribute the soils evenly and make our life much more easier. But even by doing that, we still have to do some manual work. So we spread the soil using these rakes inside the box, and then we compact the soil using the vibratory plate compactor. So in total, there were 78 lips of soil that were performed for this model box to fill to a height of 4.63 meters. And there was one round of compaction per lift. So this was calibrated in the beginning of this model preparation process. And the total mass of soil used was 339 tons of soil. And to check the density of the soil as we were building it, we performed sand cone testing and nuclear density test. So this is the result of the density test using the sand cone and nuclear density. So you can see the maximum dry unit weight distribution as well as the moisture content distribution from both the sand cone test and the nuclear density test. You can see that the sand cone test is giving a slightly lower dry unit weight as compared to the nuclear density. And nuclear density test is much more closer to what we target to achieve based on our compaction effort. As for the moisture content, it was around 5%, and it was below the optimum moisture content, which means that we compacted the soil dry up optimum. We actually did not control the moisture content for this soil, so it was as placed. Because our soil was outside in the yard, there was no any housing, so it rained. Sometimes the moisture content became higher and sometimes it was lower. But on average, it was around 5%. So this table is just the average for all the depths. And you could see that the nuclear density test is giving us around 43.2% relative density, which was close to our target of 50%. So for the instrumentation in soil, it consists of a triaxial MEMS accelerometers, the piezo accelerometers, and earth pressure cells. These accelerometers, they record the soil accelerations. We were using the two types because this has a sampling frequency of just 256 hertz, whereas these piezo ones had a sampling frequency of almost 10 kilohertz. And the earth pressure cells, they were used to measure the changes in the horizontal stress in the soil so that we could calculate the coefficient of earth pressure after shaking events. For the box, we use the LVDT to measure the relative displacement between the laminates, the top and bottom. And we use the string potentiometers to measure the permanent displacement of these laminates. Also, there was, we used the triaxial MEMS accelerometer to measure the box acceleration. And there were a total of 88 sensors with 142 data channels. So this is just a typical instrumentation layout. So the MEMS accelerometers were arranged in three arrays, one at the center, one near the box wall, and another on the box. The piezo accelerometers were only present at the center. The LVDTs were present between the laminates, so there were 19 LVDTs on the east side and 19 on the north side. And string potentiometers, we had 5 on the east and 5 on the north side. And the earth pressure cells were only present at the 9th laminate from the top. Okay, so I'm moving on to the input table motions. So I used white noise and wavelet motions to characterize the soil model. And I used 22 earthquake recorded motions and 11 sinusoidal motions. So in total, there were 173 shakings that were performed on the soil model. So this is a table that shows the list of motions. And these earthquake motions, they were performed in both X, Y, and XY directions. And for this presentation, I'm going to focus on the white noise and the recorded earthquake motions only because of time limitations. So first, I would like to present the settlement of the soil surface as we shook the model. So the settlements were measured at 13 marker points, as you can see in this schematic. And they were measured like manually using a laser and a tape, so they are not so accurate. And here you see the settlement plotted versus the different shaking events. So they were performed after the shaking events. That's why we have an A here. The settlement, cumulative settlement at the center, we had around 35 millimeters. And whereas considering all the markers, we had around 28 millimeters. So The soil did not settle that much in our test. So the next result is related to the site period of the soil model. So this was determined using the white noise excitations that were performed after the strong shakings. So for this, I computed the frequency response function based on the accelerometers AC1 and AC9, the top and bottom, to find the natural frequency as well as the site period. So this plot shows the period of the soil model based on different shaking sequence number. So these were performed for both the X direction and the Y direction. So I didn't see any appreciable difference in the site period based on the shaking event and also based on the X and Y directions, and a mean value of around 1.45 was obtained. Next, I estimated the shear wave velocity of this soil model. So this was estimated based on the travel time of the wavelet motions from the bottom accelerometer to the top accelerometer. And these were also performed after the shaking events. So I used two methods to estimate the travel time. One is the cross correlation between these two acceleration readings, and the next is the time history analysis based just the difference between the time between these peaks in this wavelet motion. So, so using this time difference, I could estimate the shear wave velocity, which is Vs. So here is the average Vs of the soil model based on different shaking sequence number, and we did it for cross correlation and time history. So similar to the site period, we didn't see much of a difference across the different shaking events, and a mean value of 135.6 was obtained. And I also calculated the period of the soil column based on this Vs, and then compared with the Fourier analysis that is from the white noise, and it shows very good results, like very comparable results. So we have a second degree of verification. So this is a video of the 1D shaking. Is it a Loma-Prieta-Gilroy motion, the side view, top view, and the table acceleration. Yeah, but it's not that in scale, but yeah. So this is just shaking in this X direction. And I think the video file was big, so sorry. Okay, I think we have it.
You need to click on it or something?
Yeah.
So we'll have to go outside here, and somewhere here the mouse will appear. Okay, so there it is.
Yeah.
So you want to click on that.
Yeah.
So you will notice it's over here, and then we click on this.
Yeah.
Yeah, it's like an extended screen. Says it's running well.
Yeah. Sorry, sorry about that. I couldn't show you the video.
We'll get you
Yeah.
going, yeah.
Yeah.
Maybe
But
you can tell them how many tests you did and all that, and by then they'll be able to get it going.
Oops, something happened.
Maybe just duplicate it instead of.
Yes,
I think yeah,
he's getting her.
yeah. Thank you. Yeah, sorry about that. The video could not be played, but yeah, I will just move on to the results quickly. So this is the 1D versus 2D shaking response for the spectral acceleration. So this is the response at the ground surface. And I've shown the response for the Baja California motions, which were scaled to different PGAs. And the response is shown for 1dx and 2dx in the x direction motion. So you could see that as you increase the intensity of the shaking, then you are seeing larger difference between 1D and 2D shakings. And usually the 2D shaking is showing smaller spectral acceleration than 1D shaking. Next, the response of the soil column, but this is based on the maximum shear strain profile. So these shear strains were obtained for this array of accelerometers. First of all, I double integrated the accelerations obtained from this accelerometer and computed the displacement. The displacements were then computed were converted into shear strain based on the weighted residual differentiation method. So here is the results of the shear strain profile, the maximum shear strain profile for 1dx, 1dy, and 2dxy motions. So this were also for the same Baja California motion. As you can see, if you increase the intensity of the shaking, we are seeing much larger difference between 1D and 2D shaking, meaning that the 2D shaking is inducing a stronger nonlinear soil response as compared to 1D shaking. So this is the results of 1D versus 2D shaking for all the earthquake motions. As I previously mentioned, I used 22 earthquake motions. So here I plotted the log difference between the spectral acceleration in 2D over spectral acceleration in 1D versus the period. So here is the mean curve and the plus minus 1 standard deviation curve. You could see that at periods that are near the site period, we are seeing negative log difference, meaning that the 1D shaking is larger than 2D shaking, whereas for longer periods, we are seeing a positive log difference, meaning that the 2D shaking is larger than 1D shaking. However, the difference since in this log value is showing a 10% range of this variation based on these 22 motions. So I just tried to correlate the difference between the 1D and 2D shaking by calculating the root mean square difference, and then using the peak ground acceleration as my intensity measure. And I described this correlation using the Spearman's correlation coefficient, and I got a value of 0.9, which indicates that there is a very strong positive correlation between the root mean square difference and PGA. And also I used a hyperbolic fit to this data, which gives a coefficient of determination value of 0.84. So this shows that the ground motion shaking intensity, or specifically the PGA, can be a good predictor for the difference between 1D and 2D shaking. So in conclusion, the soil, it showed minimal change with successive shaking events. And the difference between 1D and 2D shaking was related to the intensity of the shaking. The mean difference of spectral acceleration at the surface from 1D and 2D shaking showed less than 10% variation across different periods. And the root mean square difference had a very strong positive correlation with the peak ground acceleration, indicating that PGA can be a suitable predictor for the effects of 2D shaking. So in my further study, I will use these experimental results to compare with the nonlinear site response analysis using Elestina, just to validate my numerical as well as the experimental work. Thank you. If you have any questions, I'll be glad to answer them.